All right, welcome back. We are in Unit 5 of AP Calculus. This is Lesson 2, Extrema on an Interval. So first thing I like to do is describe what I call an absolute extrema, or what everyone calls absolute extrema. On the interval I, if f of c is greater than or equal to f of x for all the values of x in I, then we call it an absolute maximum. So we're just saying it's the highest y value. Maybe it ties another one, but that y value is what we call the maximum. So when we talk about a max, we're talking about a highest y value, highest f of x value. Likewise, if f of c is less than or equal to f of x for all the values in the interval, then we call it the absolute minimum of the interval. Absolute maximums, absolute minimums are also called global maxes and global mins. So I'll try and use those words interchangeably to keep you familiar with them, but I kind of tend towards calling them absolute. So now we can define relative extrema. Well, relative extrema have a little bit of a subtlety. It says if there exists an open interval AB around x equals c, where f of c is the biggest value over f of x, for all values in that interval, then we say it's a relative maximum. So in order to be a relative extrema, you have to have an open interval around you. So relative extrema, that's the first thing we wanted to say is we have to be able to construct an open interval around it. But if we can construct any open interval, no matter how small, and in that open interval, that value is the largest value, then we get to call it a relative maximum, meaning that it is in that neighborhood. Around that point, it's the tallest point. So I always think of like K2 is a really tall mountain, right? Second tallest in the world. But it's not as tall as Mount Everest. But it's a relative maximum for where it is. It's the tallest mountain around it, right? It's just not the tallest everywhere. So the difference between global versus local. Another word for relative max and relative min is local. So we'll talk more about relative in a bit. I want to talk about absolute extrema first. Actually, let's go over some definitions. Let's put some pictures of this. So f of x on the interval from -2 to 4. F has an absolute maximum. Remember, an absolute maximum is actually the y value. What is the absolute max that we reach? Well, that's 21, okay? And where does it happen? You could say x equals 4 or the point 4, 21. The x value locates the maximum, but the maximum itself is the y value. It has an absolute minimum of -15 that occurs at x equals -2. We have a relative minimum. Can I construct is there an area, a neighborhood, an open interval around which this is a relative minimum? Yeah, I can. It's the smallest point. It's a relative minimum of 1 at x equals 2. We also can do the same thing here. We can say I have a relative maximum of 5, and I'll use the point here and say 0, 5, just to show the other way. So this begs the question, could we also say that we have a relative maximum at 4? And the answer is no. Not on this interval. Now, if f continues, if we continue this graph going up, then yes. But I cannot construct an open interval containing -2 or 4 because there are no x values to the right. I can construct a closed interval containing 4, but I can't construct an open interval containing x equals 4. Because to be an open interval, I've got to get a little bit past this point. I can't put the open interval at 4 because then I wouldn't include that 4 because the open interval from -2 to 4 doesn't include 4, so that doesn't work. So no, I can't call 4 a local. I can't say 421 locates a local max. Can't do it, but it is the absolute max. All right. What I want you to do is estimate the slope, if defined, at the relative extrema for each of the functions shown. So go ahead and do that, and then try and answer the question about what must be true. All right, so let's take a look at the relative extrema here. Again, I mentioned earlier we're talking about absolute, but I want to talk about that mostly today, but I do want to make sure we understand relative extrema first. So where's the slope of the relative extrema? Well, right here, this is a relative maximum, and the slope here is 0. And the slope here is also 0, right? That's a relative max. That's a relative min. Okay, so what about here? Well, this is undefined. You might say it's vertical or something like that, but it's actually not defined at all. It's a cusp. So at this relative min, the derivative is undefined. What about here? Well, this is a relative min, and again, we have a cusp, right? undefined slope. And up here, the slope is 0. So what I think must be true about tangent line at relative max or min is that the tangent line is either horizontal or undefined. So in other words, f prime of c is equal to 0 or undefined at a relative extrema. Extrema, it means like either a max or a min. So let's define what a critical number is. For a function f and value x equals c, if f of c is defined and f prime of c is equal to 0 or f prime of c is undefined, then we say x equals c is a critical number of f. It's very important that f of c actually exists. If f of c doesn't exist, the derivative won't either. But we're talking about as a point actually on the curve where the derivative is either 0 or undefined. So critical numbers here would be here. 0 is a critical number of this function. Looks like -1.5 and 2. And then 0 because it's undefined, and like 0.8. So anywhere where there's a point where the curve is defined and the derivative is 0 or undefined, we call that a critical number. And here's the relative extrema theorem. Relative extrema occur only at critical numbers. So if I know all the critical numbers of a function, I know everywhere where the relative extrema can occur. Just don't over-apply that. Just because a relative extrema occurs, just because a critical number occurs doesn't mean a relative extrema occurs, all right? So what this is saying is that every relative extrema x value is a critical number. Not every critical number is the x value of a relative extrema. The classic example that's usually brought up is the graph y equals x cubed. It has a horizontal tangent line right here, little stasis point where it just kind of hovers for a second before going back up. That is not a relative extrema, but it is a critical number. So just be careful about that. All right, let's talk now about, this is what I wanted to get to. I'm excited to get to this. Absolute maximum and absolute minimum. I want us to derive a theorem together again, see if we can't figure this out. We're working through these theorems. We're not proving them rigorously, but hopefully I'm convincing you of their truth. So I want you to write down the absolute minimum, where it occurs, like just the points, if they exist. If they don't, just say D and E. So pause the video and try that. All right, let's start with this first one. Well, we have a minimum here at right there at 0, 1. And then we got a maximum. It's over here at, looks like 2, 1, 2, 3, 4, 5. So 2, 5. Here we had a minimum at 0, 1. And we have a do we have a maximum? I don't think so, because this is an open endpoint. 2 is not on there. Someone might say, well, right here, really close to x equals 2, we're really, really high up. But because of the infinite density of the real numbers, no matter what x value you give me, I can give you an infinite number of numbers bigger than that value, but still less than 2. And every one of those values will give me a higher and higher y value. So there is no maximum. It does not exist. What about the minimum? Well, I'm sorry, what the minimum on this one? Well, same thing. We got an open circle here. So again, I can get as close as I want, but I can never finish getting closer. So this doesn't exist. But the maximum this time does now. We have 2, 5 again. So here's a question. What conditions are necessary to guarantee both an absolute max and an absolute min? Well, I hope you get it just from looking at this. But here, this function is got a closed interval, and we are continuous on it. This function is continuous, but doesn't have a closed interval. It's not continuous on a closed interval. And then this one here, it's on a closed interval, but it's not continuous because we have this discontinuity because of the hole. So what we need is continuous on a closed interval. That's what we need. We need that. And if we have that, we know that there must exist an absolute highest y and absolute lowest y. It may not be unique. It might be like the sine curve that goes up and down, up and down, up and down, but and hit it many times, but we know it has a highest and lowest. All right. Well, that theorem has a name. It's called the extreme value theorem. And once again, it's another VT theorem. This is the EVT. And just like the IVT, it requires just CC. So this is what I call a CC theorem, extreme value theorem. If a function is continuous on a closed CC, then we know it attains an absolute max and an absolute min. Okay, how do we find them? We use what's called the Candidates Test Theorem. So to find the absolute value of extrema, the Candidates test is simply a combination of the Relative Extrema Theorem with the extreme value theorem. Okay, it says first find all the critical numbers of f. Then evaluate each one. Then evaluate at the endpoints. The smallest of those is your min, the greatest is your max. And when you work this out and cite it for your theorems, you just cite by the candidates test. And you show your work. As long as you show your work and cite candidates test, you're good. All right. So let's start with this. Find the absolute maximums and minimums of f on the given closed interval. All right, we'll start with this one. Well, is this can I use the candidates test? Is this continuous on this interval? It has to be continuous. All right, well, yeah. F is continuous on -1 to 5. Okay, cool. Let's get the derivative. F prime of x is equal to 6x minus 24. So then we'll set it equal to 0 because there's nowhere where this is undefined. And if I solve that, I should get x equals 4. So we have a critical number at x equals 4. We have our endpoints. Let's test each one. F of -1, f of 4, and f of 5. F of -1 is like 26, I think. F of 4 is, let's see here, 3 times 16 is 48 minus, 48 minus 96 is a -4. So I think that's a -49. I'm not worried too much about the arithmetic right now. And then we'll plug in 5. We got 25 to the 3 is 75 minus 120. So it's like 75 minus 120 minus 45. I think it's like a -46 or something like that. Yeah, I think it's a -46. So clearly what we have is we have an absolute max of 26 at x equals -1, and we have an absolute min of -49 at x equals 4 by the candidates test. All right, let's try the next one. Okay, f is definitely continuous here. F is continuous on that interval. We need that. That's really important. If we don't have continuity, then we could have an asymptote, and we know that at an asymptote, you could just whoop, shoot up forever and not have an absolute max. So let's take the derivative. Okay, I get 2x to the -1/3 minus 2. All right, well, clearly x equals 0 is a critical number. So f prime of 0 is undefined. The original was defined, but f of x is defined at 0, but f prime of 0 is undefined because I would have 2 over the cube root of 0. That's negative exponent, undefined. Let's see if we can solve it equal to 0, though. Well, 1 to any power is itself. So if x equals 1, this is 2 minus 2 equals 0. So we can say that f prime of 1 is also equal to 0. Those are two critical numbers. Now all we got to do is evaluate f of -1, f of 0, f of +1, and f of 8. So f of -1 is 3 minus a negative. So 3 plus 2 is 5, plus 1 is 6. F of 0 is 1. F of 1 would be 3 minus 2 is 1, plus 1 is 2. And f of 8, the cube root of 8 is 2, squared is 4. 12 minus 16. 12 minus 16 is a -4, plus 1 is a -3. So we have, I'm going to say, an absolute max here. And we have an absolute minimum here. So we have, and we know that by the candidates test. I think this would be a worthwhile one for us to graph just to take a look at. I want you to check this out. So I'm going to go ahead and bring up a Desmos here. And we're going to do 3x to the 2/3 minus 2x plus 1. So look at that relative min that we were talking about there, and got a relative max there at 1, right? 1 comma 2. Got a relative min there, but in this case, the extrema on the interval are down here and up there. So that's why they were the endpoints. All right, we got a couple more to do. This one here, we got again, it's definitely continuous. We know it is continuous on this interval. Clearly, there's no division or square root or log or anything like that. Let's get the derivative and get the critical numbers. This would give me 18x squared minus 24x. And I can solve that equal to 0. I'm just going to divide everything by 6, giving me 3x squared minus 4x. I'll factor out an x. So I have x equals 0 and x equals 4/3. So we have our candidates to test are f of -1, because that's my endpoint, f of 0, f of 4/3, and f of 2. So -1, this would be -6, -12, that's a -7. F of 0 is 5. F of 2, that would be 8 times, that's 48 minus, oof. So we're going to use a calculator for the 4/3 anyway. You would never have to be crunching stuff this bad. So I'll just say f of x is equal to 6x cubed minus 6x to the 4th plus 5. And we'll say f of 4/3. What is that? Okay, that's all right. And we've got f of 2 we thought was going to be pretty big numbers as well. -43. So this was a -43. And the other one was, let's see here, 0.259. So it looks like our absolute max is at f of 0, right? Yeah. Yeah, we did. It turns out this isn't even a min at all. We talked about that. You had a critical number, but it was just kind of this stasis point. There's our absolute max at 0.7. Did I do something wrong? Why am I getting? Did I type that in wrong? Well, hold on. Yeah, it should be 4/3 should be my. Well, what am I doing wrong here? Well, they're saying the max is at 3/4. What did I do wrong? Oh my goodness. This was a cubed. So the x should have been here, not here. So it should have been 3/4. Which would make this, that definitely will be the absolute max at, so 3/4. I was rushing along too much. 5.6. All right. All right, we've got one last problem to do here. F of x is clearly continuous on this interval. So I'll just make a note of that here, that this is continuous on this closed interval. The extreme value theorem then tells us that that f must achieve an absolute maximum min, which we can find using the Candidates test. So first we take the derivative. Remember, this is sine of x squared like that, right? So I need to use my power rule and then the chain rule. So this is 2 sine of x times the derivative of sine of x, which is cosine of x. Then the derivative of cosine of x is a negative sine x. We'll set that equal to 0, and I'll factor out a sine x. And then I have 2 cosine of x minus 1. So when does sine of x equal 0? That's going to happen at x equals 0, at x equals pi, and x equals 2 pi. But we already have those for our endpoints, right? And when does cosine of x equal 1/2? Well, that's going to happen at pi over 3, and 5 pi over 3. All right, let's go ahead and evaluate then. So let's do f of 0, our first endpoint. That will be 0 plus 1 is 1. F of pi, that'll be 0 minus 1 is a negative 1. And then we'll do f of pi over 3. Well, the sine of pi over 3 is square root of 3 over 2, but then we square it. So it becomes 3 over 4. And the cosine of pi over 3 is a positive 1/2. So this becomes 5/4. All right, then let's do f of 5 pi over 3. Okay, well, let's see here. The sine of 5 pi over 3 is a negative square root of 3 over 2, but we're squaring it. So it becomes, again, just 3 over 4 plus 1/2, which becomes 5 over 4. So it looks like we have two places where we have an absolute max at pi over 3, 5 pi over 4, and 5 pi over 3 at 5 over 4 as well. We definitely have an absolute min. And our absolute min is at pi comma negative 1. And let's just briefly look at the graph. Okay. So I've got that graphed here. And we can see, let's see, here we have, there's that max, there's that max. We got a min at pi negative 1. Okay, that's all. So until next time, take care.